All right, let's take a closer look at acceleration. Another one of our basic ways of describing the motion of an object. So far we have distance and displacement, speed and velocity, and now we're adding acceleration to the mix. Unlike the previous two where there was a separate component, a scalar and a vector way of doing it, there is only one way to do acceleration. Acceleration is always a vector quantity because it's based on velocity. Is defined as rate of change in velocity. And because it's a velocity-based concept, because it's based on a vector quantity, it too is a vector quantity. And as you know, with vector quantities, we mean both magnitude and direction. We need to know the number with the unit, and we need to know direction. But this time, direction is not handled with north, south, east, west, up, downs, left, rights. Direction is handled with the positive or negative sign. It's based on the sign. Positive acceleration means that an object is speeding up. This happens when the direction of the acceleration is the same as the direction of the object. So instead of having to say things like the object is moving to the right, it's being accelerated to the right, and having to deal with the directional parts being the same, telling us it's speeding up, we look at the sign of the acceleration and we see that it's positive, and the positive tells us it's speeding up. A negative acceleration is slowing down. And again, it takes the left, rights, up, downs, instead of having to worry about it moving to the right, accelerating to the left, realizing that those are opposites, knowing that opposites mean slowing down. We just look at the sign. And the sign is negative, and we'll know that the object is slowing down regardless of which direction it's moving. So again, it kind of simplifies the direction thing. It is a vector quantity, but you're not going to see any north, south, east, west, up, down, left, rights on it. You're just going to look at the sign. Positive accelerations mean speeding up, negative accelerations mean slowing down. The equation for it that you're taught in physical science is Vf minus Vi over T. But because we have to do things algebraically in physics, we'll learn acceleration is change in velocity, delta V, over change in time, delta V. And that change in velocity, like any other change, any other delta, is the final minus the initial. So it's Vf minus Vi. And this allows us to work with it algebraically a little easier, not having to worry about orders of operation, making sure we're doing our rearrangements correctly, that kind of thing. Whenever we're solving for a final velocity or initial velocity, we'll solve for the change in velocity first, and then we'll use the delta V equation to figure out what either that final or that initial was. Units are kind of weird on this because you'll have some kind of velocity unit on top, like meters per second, and on the bottom you'll have some kind of time unit. And this time, those time units don't have to match. So your velocity can be miles per hour, but your time can be in seconds, and that's okay. We don't have to worry about converting any of that. We would just incorporate that information into the unit for our answer. We do have to make sure the two velocities are the same. Obviously, we can't have one in miles per hour and the other one in feet per second. We would have to make sure those are the same, but that's odd that you see one problem set up like that. Typically a lot less to worry about with unit conversions on acceleration questions. So let's take a look at the problem. A car on an on-ramp accelerates from 20 miles per hour to 60 60 miles per hour in 5.4 seconds. What is the acceleration? So again, just like any other problem, we want to take that same problem-solving approach. We want to look at all of our numbers and figure out what those are, label them. 20 miles per hour, that's a v. We'll get into whether it's f or I in just a second. 60 miles per hour, that's a v. Now I want to say these do look like just speeds because there's no direction on them. But it's implied that these are positive, so we're handling the directions that way. We're not worried about north, south, east, and west on these acceleration problems. It's the sign that's going to dictate direction. And then our time, our delta v, or delta t, is 5.4 seconds. We're looking for acceleration. That's our unknown. So again, just like we would any other problem, we're looking through trying to figure out what the numbers are, what the unknown is. Now, this has that extra step of figuring out which v is f and which v is what, or I. To do that, we actually have to look back at the question again and look for some key words. One of the easiest ones to spot is the word to. The word to tells you where you're going. If you're going to the office, that means you're going to end at the office. If you're going to the bathroom, that means you're going to end at the bathroom. We're going to 60, that means we're going to end at 60. It's F. That must be I. The next thing we're going to do is calculate our delta V. Whenever you're trying to find the acceleration or whenever you're trying to find the time, start by finding delta V. And again, any delta is always the final minus the initial. When you're doing slopes, rise over run, it's YF minus YI. It's XF minus XI. It's always final minus initial when you're doing a delta. And that's important because this is what's going to give us our sign for our answer. So my final is 60 miles per hour. My initial is 20 miles per hour. My delta V is going to be 40 miles per hour. And more importantly, it's positive 40. That positive is going to tell us what the direction of our acceleration is going to be. This is where the sign is going to come from. If it's negative, it would end up being negative here. Again, these units do have to be the same. So we can subtract, combine those units together. If one were in miles per hour and the other one were in feet per second, you would have to make them match. Like I said, you don't see that too often. Once we have our change in velocity, we're ready to calculate. Delta V over delta T. Our delta V was 40. My delta T, 5.4 seconds. Number-wise, it's 40 divided by 5.4. And that's 7.4. Again, I'm rounding. Now we need to put a unit on there. And the unit is a combination of what we see here. Always start with the unit that's on top, so it's miles per hour. And then add another slash and put the unit that's on the bottom. In this case, seconds. So the unit is miles per hour per second. If these two time units are the same, if these would have been both hours, we could simplify that into hours squared. But when they are different like this, we do have to write them both out. Even if they were the same, we could write them both up there, miles per hour if we wanted to.
The FCA meeting will begin shortly. Again, all students, FCA meeting will begin shortly.
All right, now for the algebra part, because this is physics, and you're expected to be able to solve for any of the variables that are in a problem. And as I mentioned, we're doing it in this very specific way because of the algebra. Let's say car accelerates at a rate of 7.5 miles per hour second for 6 seconds. If the initial speed or velocity of the car is 15 miles per hour, how fast will it be going when it's done? So again, just like any problem before, we go through and figure out what all these numbers are. So I get 7.5 miles per hour per second. I got 6 seconds. And I've got 15 miles per hour. Miles per hour per second is an acceleration unit. It's got 2 times in it, or it will have time squared depending upon whether it was simplified or not. Six seconds is a delta t. And 15 miles per hour is a v, again, either f or I. This time it does say initial in the question, so we know that's I. We want to figure out how fast it'll be going when it's done. So we are looking for VF in this problem. Whenever you're using this algebraically, particularly when you're solving for VF or VI, there's a really good chance you're going to do things in the opposite order. In the first one, we used the delta V equation first, found out what the change in velocity was, but because we're lacking one of our velocities here, we save that equation for the end. We start with the acceleration equation this time. Delta V over delta T. And again, what we're going to do is we're going to solve for delta V first. And then we'll use that equation at the end to figure out what the final velocity was. So 7.5 miles per hour per second. Is equal to delta V over delta T, which is 6 seconds. Solve for delta V. So what we're going to do, since we're dividing by 6 seconds, we'll multiply both sides by 6 seconds. 6 seconds cancels out over there. Math teachers like when you flip the delta V to the other side. 6 times 7.5 is 45. The seconds are going to end up canceling. And we end up with just miles per hour. Now that's not the answer to our question, that's just the change in velocity. To find the answer to our question, now we have to use the delta V equation. VF minus VI. This is the delta V, 45 miles per hour, is equal to VF minus VI, which was 15 miles per hour. Opposite operations again, because we're subtracting by 15, we'll add 15 to both sides. Solve. Cancel out completely. VF is 45 plus 15, which is 60 miles per hour. So we did this in the exact opposite way we did the previous one. The previous one, because we were solving for acceleration, we did the delta V problem first. And then we took that number and used it in the acceleration equation. In this one, because we were solving for one of our velocities, we had to save the delta V equation for last. Use the acceleration equation first, figure out what the delta V is, and then use the delta V equation to find our missing one. You do the same thing if you were looking for a VI. You'd solve in the same order. If you're solving for a delta T, then you're back to what we did the first time. But we do have to be careful of variable in the denominator there. Car accelerates at a rate of negative 3.2 miles per hour per second. The car has an initial speed of 15 miles per hour. How long will it take it to stop? Again, like every physics problem, it starts by figuring out what your numbers are. We have negative 3.2 miles per hour per second. Those two time units tell me that that's an acceleration. And that negative is important. That's the direction. And again, it tells us already we're slowing down. We have 15 miles per hour. That is a velocity of some type. And it does say initial. So that's I. We're looking for how long it will take it to stop. We're looking for delta T. Now, at first glance, it looks like we're missing a number. We know we need a VF and a VI, but we only have one. That's because there's an implied number in this, and that happens a lot of times in physics. There's a number you need to use to solve a problem that's just not written in the equation. We're coming to a stop. So my second V, my VF, is 0. So be careful of that. It looks like you're missing a number and you don't have all the information you need. Sometimes you may truly be missing a number. Sometimes I make mistakes when I'm typing questions and I leave something out. But a lot of times it's just there's an implied number. There's a number that you're supposed to assume is there. It's just not written there. Happens a lot of times with things that are starting at a stop or coming to a stop. It happens a lot of times with falling objects where the acceleration is assumed to be 9.8 meters per second squared. So there's a number of times this shows up. Again, we're going to go ahead and find our delta V first. Delta V equals VF minus VI. My final velocity is 0. My initial velocity is 15. My delta V is negative 15 miles per hour. And that negative side is important because if that negative sign is not there, then your signs aren't going to cancel out correctly, and you're going to end up with a negative time, which we can't have. So that negative is important. It's going to end up canceling out the negative in our acceleration, so we get a positive answer for time. Acceleration equals delta V over delta T. So again, our acceleration is negative 3.2 miles per hour per second. Our delta V is negative 15. And our T is what we're looking for. Remember, whenever you have a variable in the denominator, your job is to get it out of the denominator. Multiply both sides by delta T to do that. Cancels it out on the right and moves it to the left. So I can rewrite this equation as negative 3.2 miles per hour per second times delta t equals negative 15 miles per hour. Since we're multiplying by negative 3.2, we'll divide both sides by negative 3.2 to solve. So I end up with delta t equals 15 divided by negative 15 divided by negative 3.2 is 4.68. I'm just going to round that to 4.7 because we're dividing two negative numbers. We ended up with a positive again. That's why that negative is so important in the delta V. The miles per hour cancel and the seconds move up. It's 4.7 seconds. Again, there's not quite as much unit conversion to deal with here. Potentially, it could come up with the times, making sure that they're what you need. But ask how many hours it takes to do something, and it gives you a time in minutes. There might be a time conversion to do there. These two have to be the same, and they have to match the acceleration one. But again, I don't see a lot of practice sheets. I don't see a lot of test questions that involve any unit conversions with acceleration.